Okay, strap yourselves in, folks, because this time we're going deep, deep into the wild world of magnetism. And I'm talking way beyond your high school physics class. We're diving headfirst into excerpts you sent us from a book called Uncovering the Missing Secrets of Magnetism by this guy, Ken L. Wheeler. And let me tell you, he does not hold back.
He really doesn't, does he?
This guy is like next level passionate about magnets. We're talking full-on Tesla level conviction here. He basically says everyone else has got it wrong about magnetism, like everyone, even Einstein.
Yeah, he doesn't seem shy about calling out the big names, does he? But that's what makes this deep dive so interesting, right?
Right, like is he onto something? Is there more to magnetism than we're being taught in textbooks? Because he makes a pretty compelling case.
He does, and even if you don't agree with everything he says, he definitely gets you thinking and questioning, which is always a good thing.
Absolutely. So to kick things off, the big idea that Wheeler keeps coming back to is this. Magnetism, i.e. the dielectric field.
It's his mantra.
Yeah, like he wants to throw out all the textbooks and rewrite physics around this one concept. But honestly, when I first read that, I was like, okay, hold up, time for a little refresher here.
Yeah.
So for those of us who haven't thought about dielectric since, well, high school physics, what are we even talking about here? What is a dielectric field?
Okay, so in simple terms, you know how a battery stores energy, right?
Right.
The dielectric field is kind of like the storage space for that energy. It's all about potential energy.
Okay, I'm kind of following. So how does that relate to magnetism?
Wheeler says we get so caught up in the visible effects of magnetism, the push and pull, the way magnets attract or repel each other, that we miss the invisible force, the energy field that's actually driving the whole show.
So he's saying it's like looking at a horse's rear end and thinking it's the head, right?
Yeah.
That's one of his analogies. And it kind of threw me at first, but
Zip it out there.
it is, but it makes sense. Like, don't mistake the effect for the cause.
Exactly. Don't just focus on what you see. Look for the underlying energy that's making it all happen. Wheeler argues that the dielectric field is that underlying energy for magnetism.
Okay, I think I'm starting to get it. So it's not just some random force field. It's connected to energy itself.
Exactly. He even uses it to explain how lasers work.
Lasers. Now we're talking. How do lasers fit into all of this?
Well, he actually calls magnets field lasers.
Field lasers. Okay, now I need to hear more about this. What does that even mean?
So think about what a laser does. It takes ordinary light, which is kind of all over the place, and aligns it, focuses it, to create that really powerful beam.
Right, like a super concentrated beam of light.
Exactly. Wheeler believes that's what magnets are doing, but instead of aligning light, they're aligning this invisible dielectric field.
Okay, so instead of a beam of light, you get a magnetic field. It's like the magnet itself isn't creating the magnetic field. It's just focusing something much bigger that's already there.
That's the general idea, yeah. And the key to this whole alignment process, according to Wheeler, is something he calls the dielectric inertial plane. Most people just call it the block wall.
The what wall?
The block wall.
Okay, you've totally lost me. Block wall. What is that?
You know how a magnet has a north pole and a south pole?
Right, like the two ends.
The block wall is like the dividing line between those two poles.
Oh, okay. Like the equator of a magnet.
Exactly. But Wheeler says it's not just some arbitrary line, it's where the dielectric field is at its strongest. Almost like a spinning disk of energy that's driving the whole magnetic system.
Hold on, are you telling me there's this invisible spinning disk of energy inside every magnet? This is starting to sound like a sci-fi movie.
Well, that's Ken Wheeler for you, always pushing the boundaries.
So this dielectric inertial plane, this spinning disk, this is where the magnetic field actually comes from.
That's what he believes. And it leads him to an even wilder claim, something that really challenges the fundamentals of physics.
Oh boy, here we go. Let me guess. He says magnetic attraction doesn't even exist.
You've been reading ahead, haven't you?
Maybe a little. But seriously, no magnetic attraction. Come on, how is that even possible?
I know it sounds crazy, right? But stay with me here. To understand Wheeler's reasoning, we need to go back to that bathtub analogy, the dielectric field, as a bathtub full of water.
Okay, I'm picturing it. Water, bathtub.
Now imagine you pull out the drain stopper. What happens?
Well, the water rushes in, right? It forms like a whirlpool around the drain.
Exactly. And that's kind of how Wheeler sees magnetic attraction, or at least what we perceive as attraction. He's saying that instead of two poles pulling towards each other, there's this low-pressure zone in the dielectric field between them, like that drain you just pulled.
So the poles aren't actually attracting each other. They're being pulled towards this dielectric drain.
Oh, that's a great way to put it. It's this avoidance effect, things moving towards a lower pressure point in the field.
Okay, I kind of see where he's going with this. But isn't that how gravity works too? Things being pulled toward a center of mass.
You're picking up on the connections Wheeler's making? He actually draws a direct parallel to gravity.
Oh boy, here we go. So he's saying gravity is just a giant dielectric drain. I mean, what about Einstein and warped space-time and all that?
Well, Wheeler has some thoughts on Einstein, too.
I bet he does.
He sees those theories, particularly the concept of space-time curvature, as, well, a little too complicated.
It's complicated.
Yeah, he thinks they're missing the fundamental point, which he believes is this all-pervasive dielectric field.
So while everyone else is busy warping space-time, Wheeler's over here saying, nope, it's all about the dielectric field.
That's pretty much the gist, yeah.
Okay, so if Einstein got it wrong about gravity, what's Wheeler's alternative? What's causing this dielectric drain on a cosmic scale?
He calls it the ether.
The what? The ether.
Yep, like that old scientific idea, an invisible medium that exists throughout all of space.
Wait, you mean like those old illustrations with the swirling lines representing an invisible energy field? That ether.
Oh, one and only. And Wheeler believes it's making a comeback.
Hold on. I thought that idea died out a century ago. Didn't they do an experiment, the Michelson-Morley experiment or something, that completely disproved the ether?
They tried to, but Wheeler argues that the experiment itself was flawed. He says there's actually plenty of evidence for the ether if you know where to look.
Okay, you've piqued my curiosity. What kind of evidence are we talking about? Give me an example.
Well, think about light, how it travels through space.
Okay, light travels through space.
It travels as a wave, right?
Like a wave on the ocean.
Exactly. And just like those ocean waves need water to travel through, Wheeler says light waves need a medium too. They need something to wave in, and that something is the ether.
So he's saying space isn't actually empty. It's filled with this invisible stuff that allows light to travel.
That's the basic idea, yeah.
I'll be honest, that's pretty out there.
It is, but it gets even wilder. Wheeler believes that if we can figure out how to tap into this ether, we could unlock incredible new technologies. Things like faster-than-light communication, new forms of energy, maybe even manipulating gravity itself.
Whoa, hold on. Faster than light travel? That's straight out of Star Trek. Is any of that even remotely possible?
It's definitely on the fringes of theoretical physics. But Wheeler is convinced that the ether holds the key to achieving things that seem impossible right now.
Okay, let's say, for argument's sake, that I buy into all of this ether idea. If this ether is so powerful, so fundamental to the universe, why haven't we detected it? Why isn't there any hard evidence for it?
Well, that's the million-dollar question, and it's one that Wheeler wrestles with, too. He believes that mainstream science has become, well, a little too stuck in its ways.
Stuck in its ways how?
Too resistant to new ideas, too focused on the established models to see something truly revolutionary. He sees himself as kind of a lone voice, a maverick, challenging the status quo.
Like a modern-day Galileo.
Exactly. He's not afraid to ruffle some feathers, especially when it comes to questioning the accepted narratives about how the universe works.
And that brings us back to bismuth, right?
You know,
Because that seemed to be a big theme in what we were reading from Wheeler. He seems, I don't know, almost obsessed with this element.
he is, and for good reason. He thinks it's the key to everything.
The key to everything. You mean the key to understanding the dielectric field?
Exactly. He believes bismuth holds the potential to unlock the power of this dielectric field.
Okay, now I'm really lost. We were just talking about the ether and faster than light travel, and now we're back to bismuth. What does bismuth have to do with any of this?
Okay, so we know bismuth is a metal, right?
Right. Kind of a weird one, but yeah, it's a metal.
But it's not magnetic like iron or nickel. In fact, it's quite the opposite. It's what we call diamagnetic.
Diamagnetic. You mean like it's repelled by magnets?
Exactly, like those cool videos you see online where a piece of bismuth is levitating above a magnet. That's diamagnetism in action.
Okay, I've seen those. They're pretty cool. But what does that have to do with the dielectric field? I still don't see the connection.
Well, Wheeler believes bismuth's diamagnetic properties are a direct result of its unique relationship to the dielectric field.
Okay.
He actually calls it a dielectric dynamo.
A dielectric dynamo. That sounds intense. Why does he call it that?
Remember how we were talking about the dielectric field being like a spinning flywheel of energy?
Yeah, the stronger the field, the faster the flywheel spins.
Right. Well, Wheeler argues that bismuth is like a supercharged flywheel. It has incredibly high dielectric inertia.
Dielectric inertia. What is that?
It basically means it resists changes in the dielectric field, like a really heavy flywheel. And Wheeler claims that if we can figure out how to shape and manipulate bismuth in the right ways, we can tap into this enormous energy potential.
Wait, you're saying we can get energy from bismuth? How?
No, he doesn't go into a ton of detail in these excerpts, but he mentions something called programmed bismuth disks that he's been experimenting with.
Programmed bismuth disks. Okay, now that just sounds like something out of a science fiction novel. What does that even mean, to program bismuth? Program bismuth disks? Dielectric dynamos? I'm starting to think we need a whole glossary of terms just to keep up with this guy.
He definitely has his own unique vocabulary, that's for sure.
But that's part of what makes this so fascinating, right? Is like we're getting a glimpse into a whole new way of understanding the universe. But, okay, let's say, for argument's sake, that bismuth really does have all this untapped potential, like Wheeler claims. Why aren't we hearing more about it? Why aren't scientists all over this?
Well, that gets to the heart of Wheeler's argument, doesn't it? He believes the scientific community is just, I don't know, too set in its ways.
Too stuck in the old paradigm?
Exactly. Too focused on what they already know, on the accepted models, to see something truly groundbreaking, truly revolutionary.
So he sees himself as kind of like a lone voice in the wilderness, shouting about this amazing discovery that everyone else is ignoring.
That's one way to put it.
I mean, it's a compelling narrative, right? The maverick genius versus the rigid scientific establishment. But it also makes you wonder, if bismuth is so special, why hasn't anyone else figured this out?
That's the question, isn't it? And it's one that Wheeler tries to address. He argues that it all comes back to this fundamental misunderstanding of the dielectric field.
So we're back to the dielectric field again. It always seems to circle back to that.
It does, because Wheeler believes that once you understand the dielectric field, everything else falls into place.
Okay, so for those of us who aren't planning on building our own dielectric dynamos anytime soon, what's the takeaway here? What can we learn from all of this, even if we don't fully understand the science behind it?
That's a great question. And I think the biggest takeaway, for me at least, is the importance of questioning assumptions. Whether or not you agree with all of Wheeler's conclusions, and some of them are definitely out there, he forces us to re-examine what we think we know about the world. He reminds us that even the most basic, most fundamental concepts, like magnetism, might have more to them than meets the eye.
It's like that saying, the more you learn, the more you realize how much you don't know.
Exactly.
Well, I have to say, this deep dive has definitely opened my eyes to a whole new side of magnetism. I never would have thought that something as seemingly simple as a magnet could be so complex, so mysterious.
It just goes to show there's always more to discover, always more to learn.
Absolutely. Big thanks to you for joining us on this deep dive into the mind-bending world of Ken Wheeler and his theories on magnetism.
It's been my pleasure.
And to all our listeners, keep those questions coming, and we'll see you next time for another deep dive into the mysteries of the universe.